Következő előadónk pedig Fabien Wernli lesz, aki Franciaországból érkezett hozzánk, mégpedig a Francia Nukleáris és Részecske Kutató Intézet munkatársa, ahol rendszermérnökként dolgozik. Fabien egyébként az open source megoldások elkötelezett híve, számos külföldi konferencia neves előadója, és például a devops.com-on is jelent meg a publikálásában nemrégiben egy nagyon jó kis technical tutorial, ezt javasoljuk mindenkinek elolvasásra, a témája hasonló lesz, mint amiről Fabien most előad nekünk. Fabien egyébként svájci származású, 4 nyelven beszél, a magyar még nincs közte, de már 6 órája Magyarországon tartózkodik, és elég gyorsan tanul, úgyhogy reméljük, hogy hamarosan ez is közte lesz.
És akkor néhány szó az előadásról. Tartozom egy vallomással, amikor a Balabithez bekerültem vérbeli szekuritásként, akkor rögtön az első meetingen jöttek a kollégák, és mindenféle egzotikus szavakkal kezdtek el dobálózni, hogy Hadoop, meg Elasticsearch, meg Kibana, és azóta igazából rááll a szemem ezekre a dolgokra, és úgy látszik, hogy az egész világ valahogy ezekkel a szavakkal dobálózik, tehát a security-ban én egy kicsit lemaradtam ezekkel a témákkal. Viszont elolvastam Fabiennak az előadását, amikor készültem ugye itt a moderálásra, és azt láttam, hogy ezeket a kulcsszavakat használgatja, úgyhogy erősen bízom abban, hogy egyrészt meg fogom érteni én is, hogy tulajdonképpen ezek a technológiák miről szólnak, másrészt pedig egy gyakorlati összefoglalót kaptok arról, hogy tulajdonképpen abban a hihetetlen mennyiségű loghalmazból, amit például a syslog-ng-vel lehet összegyűjteni, hogyan lehet értelmezhető, struktúrálható, értelmezhető, felhasználható adathalmazokhoz jutni az üzemeltetés során, és hát erről fogjuk majd Fabien előadását meghallgatni. Fabien, please.
Hi. So, does everybody hear me? Yes. Okay. So I can only agree with what you just said because I didn't understand the word of it. So I begin to apologize. I'm doing this in English because obviously I don't speak Hungarian. Okay, my name is Fabien Wernli. So it's a Swiss name, but I live in France. This is my email, and I am a sysadmin. I've been working at CCI In2p3 now for almost 10 years. So this is not working. Why? Okay. So CCI In2p3 in Lyon. It's a data. We have basically a data center for French academic research. Most of our users, so 85%, are from the LHC experiment at CERN, the Large Hadron Collider. I'm going to speak a little bit about that later on. We have about 20,000 logical cores to do computation. We have about 20 petabyte of tape used. We can go up to, I think now it's 350 petabyte possible. And we have around 10 petabyte on hard disk. So our computing center has been around for quite some time in France, and the historic clients were from the physics, high energy physics community. But recently, and very recently, we have quite enlarged our user base. So you can see some of the users on the map, but mostly our capacity is being used by the LHC. So the LHC is a very large, for those who are not familiar with it, is a very large collider, particle collider, or it's basically underground tunnel, which is 27 kilometers long. So you can go on Google Maps. You can actually walk around the tunnel. I'm not going to walk 27 kilometers, otherwise the talk will be a bit too long. And you can also, so this is a tunnel where you have the beams, the proton beams going through, and on the other slides we have actually the detectors. So I'm not really. It's somewhere around here. I should see it because it's one of the biggest detectors on Earth. So I should be able to find it. Oh, there it is. Yeah, there it is. You can see it here. The other ones are similar. So in these big caves, actually the beams come together and create large collisions. And that's what the physicists are, of course, tracking and looking at. So these people are actually creating a lot of data. They are creating so much data that their own computing facility cannot handle the load. Just to give an idea, from one of the detectors, we have about 1 petabyte per second coming out. So this is impossible to handle using just one data center. This is where we come in. We are one of the 12 first-level data centers to process this data from LHC. On the picture on the left, you can see the old data center, our old data center, and the new one being built. So it has been completed in 2011, I think. And some pictures are available. You can see on the top one finished bale of computing nodes. And on the bottom, you can see we have some space left to handle, to add new cabinets. Currently, we have 24 cabinets, and we are planning to have 240 before 2019. So I'm not going to speak about all this. What I want to speak about is the project I've been working on the last year, which is logs and metrics, logs and performance data, which are coming from our data center and which we are collecting or receiving, and of course, which is a lot of data. We just call them events. There are logs, which are basically text-based stuff, and metrics, which are numbers, but we just call them events, and they are more or less handled using the same systems. How many sources are we talking about? We have around 400,000 metrics, which we collect on a regular basis, mostly every 15 seconds. We have around 2,000 physical nodes, 200 power dispatching units, also air conditioning units, UPSs, and even a generator, which is sending some data. And of course, a lot of applications from the physicists and other researchers. But how much data does that actually generate? As far as logs are concerned, we have about 2,000 per second, usually, and it can go up a lot more, tenfold. And for the metrics, it's more stable because we pull them, we grab them, so it's constant. It's about 10,000 per second. So that's about 1 billion per day. We have about 1 billion events per day we need to process. So if we go back to LHC, they generate the same thing about every second, so it's not comparable. But still, it's a lot of data per process for us, sysadmins. Examples, so for logs we have, I hope you can see this, we have some kernel messages from Linux. The first one is the killer, the second one is from a device driver, and we have some application sending logs. Then as far as the metrics are concerned, we have 3 examples here. One is CPU, which is the idle part of the CPU, 99%. We have disk usage, and we have interface statistics. What we can see here is that we don't only have the value, we also have a state, okay or critical. We'll come back to that later. What do we do with all these logs and metrics? I basically see 2 use cases. The first one is a use case for the on-call engineer who wants to know immediately what's happening in the data center, and the other one is post-incident analysis. Like something broke, how did it break, why did it break? The first reason is to be informed in real time what's happening, and the second one is understand and learn and predict, learn to predict the next time something happens. So how? What can we do with all these, with these billion events every day? I'm going to show you how we used to do it. Logs can look something like that. So this is just a stream. It's a slow motion, actually, with all these logs coming in every second. They are nicely colorized by a tool from someone in this room. So it's nice. We can see the dates. We can see some parts of it which are red, which means it's bad. But we don't really, for a human eye, it's not very interesting. We can also look at each host separately, where we see that the workload is a little bit smaller per node. But still, it doesn't make sense to look at data that way. Swatch is the tool we use to analyze the logs and send alerts. It doesn't scale very much. The human eye doesn't scale either. And all this requires shell access. It means connecting to a machine, look at the logs, and do something with it. What about post-incident analysis? We used to do something like that. We used to use syslog-ng. We still do. But we used to store all the logs on a per file basis, maybe one host per file per day. And for example, looking for some failed disk events, we could grep in the log files, which was not ideal because grep is awfully slow. The file system is awfully slow for doing that kind of stuff. And you also require shell access. So if you want people to look at their logs, they need to log in. The only advantage I can see from that is the low storage footprint. We used to have all these logs compressed, and it took about a few gigabytes. So the idea is I needed a new tool to do my job. So I wanted to search for the perfect tool to do that, to scale up with all these machines and all these logs. But it can be challenging to find the right tool. So about 1 year ago, I started looking for these things. There's many tools available, open source tools. There's so many, and there's so many ways to, assemble them. You can send from one to another or the other way around, and it depends what you want to do. Basically, if you're Googling what to do with 1 billion logs per day, you find there's not 2 people doing the same thing. So it was a bit unsettling at first. So I had these different tools I wanted to try out, and I started looking at them, trying to assemble them differently. So what I'm going to present you now is what we came up with. The solution we retained was this one. It includes three basic tools, which are Riemann, syslog-ng, and Elasticsearch. So these are all open source tools. And these are a nice trinity of logging, like the title of my presentation. So I'm going to show you a demo of these tools, what we can do with them. Still, for those 2 use cases, remember the real-time stuff and the post-mortem analysis. So I hope my Wi-Fi stays on. So I'm going to try to show you some things. So this, where's my mouse pointer here? This dashboard basically is the web interface for Riemann. It's called Riemann Dash, and it's showing actually what right now the people in my data center are looking at in the control room. You have a control room with 3 screens, which are supposed to show people what's happening. So right now we can see two hosts with empty or almost empty file system. So that's a perfect example of what can be happening. On the bottom we can see the number of events coming in per second. So these are all potentially coming into my web browser. This is a web browser. So the tool is available through a web browser, and the events basically are emitted by the host, file system full, captured by syslog-ng, sent over to Riemann, and directly into the web browser using WebSockets. So it's really, really real time. I could show you this, but I'm sure this would fail, but I could connect to a machine, fail to the connection, and I would see appear here directly the login which failed. So on this dashboard, I can see basically failed logins on the right. And on the left, I can see all the users which are connected through shell access on our interactive machines. On the bottom, you can see the total. There are 313 people connected. And we can see some bad guys trying to get in using root. But of course, we don't let in people who try to log in using root. So the first dashboard I showed you is really the one people are looking at. It's the problems. Whenever there's a problem, it appears there. And the other dashboards are just experiments I did, so people can know if they think there's something going on with, for example, our OpenAFS farm. They can look here and try to see some things. For example, here we can see all the OpenAFS file servers being accessed, and we can see the volumes which are mostly used currently. We can also see something maybe more which everybody here will understand because they're using that kind of stuff, like seeing metrics on the dashboard, like RD tool or cacti, whatever. So on this dashboard, where there's currently no data coming in right now, right there are the metrics. We can see a single host, which is, by the way, OpenStack machine. And we can see CPU usage, memory usage, stuff like that in real time, which means if I log onto the machine, I just run something, I can see immediately the effects of my actions. I can also look at Elasticsearch dashboard, which is a bit small on this screen, but I'm just going to let it run so we can see the data coming in. So this is really the interface we're providing for the real-time stuff. And for the moment, it works quite well. Then we have the Elasticsearch cluster. So this is for storing all the stuff. Currently, we only store the logs, not the metrics. The metrics are still stored in RD tool. But the logs are all stored in Elasticsearch. So it's basically a cluster of machines which stores all the logs and indexes the logs. So all logs are indexed using key value pairs. So on this dashboard, for example, I see all the logs. So I can see in the 12 last hours, there are that many logs. So this is just a representation of the number of logs per every 5 minutes. If you want to see what these logs actually are, I can go down and I can actually see the logs here. Or not, because the screen is too small, but let me click on one. For example, here is just one log entry. It's a DHCP request, okay? And we can see that we extracted some values like the host, the interface, etc. So this is the indexing part. We're indexing different kinds of stuff. I'm going to explain later how this is done. Anyway, we have this nice graph here, and we can actually go and zoom into the logs, see what happened. We can identify peaks and actually go in to see what actually happened. So this is really the high-level interface we are looking at, dashboard. Then we can, as before, using real-time, we can have one dashboard per use case. For instance, I was speaking about failed logins. I have a dashboard which displays all the logins into our facility. So one curve is the succeeded logins, and one curve is the rejected logins. And then we have breakdowns by username, by type of machine from our CMDB, and of course, depending on the success. And then we can even look at the map to see where actually all these logins are coming from. So China has a lot because there's a lot of failed logins in China. I guess they have most of the IPs of the world, so I guess it's normal. But I can actually look at that stuff. I can only, if I click on this button, I will only see the rejected logins. which will enable me to see in time when they happened or where in the world they happened. So basically China again. Sorry if there are any Chinese people here. I'm sure it's not Chinese people, it's just people using Chinese machines trying to get in. We have all these different dashboards which people can actually create themselves. It's really Kibana, which is the interface, the web interface to Elasticsearch, is a great tool to build and explore and do your very personal dashboards that you can use to do your job and to detect stuff. So I have a lot of these. For example, I have one detecting the killer, the out-of-memory killer from Linux, and I can see a breakdown by users. So I can see the users who are using up all the memory of the machines and the program. So root.exe is a perfect example of software used by physicists, high energy particle physicists. Okay, so I'm going to move on. I can come back if you're interested later on, if I have time. So the architecture, very quickly, I won't go into details. Basically, we have all these events on the top going into an analyzer in real time and sending all the events to different backends. We have storage, we have real-time engine, and we have standard alerting, and on the bottom we have the GUI, or the CLI, the user on his web browser. The implementation, we use collectd for the metrics, syslog, basic syslog protocol for sending the events to syslog-ng, and we massively use one of the parsers of syslog-ng, which is called PatternDB, which is the one responsible for extracting all these fields from the messages like username, UID, etc. And then we send over the events to Elasticsearch for storage, Riemann for real-time query and display, and alerts via email or Nagios, and a web browser, as I just showed you. The hardware, for the moment, it's not fully in production, but almost. The analyzer is one VM. Riemann also is one VM. And so the big hardware here is Elasticsearch. You need to store these billion events somewhere, and the queries need to be fast. So this is where the hardware and the money is going. So I'm going to be speaking about this analyzer part, the central analyzer part, which is based on syslog-ng and PatternDB. So every event is analyzed and normalized, which means we have a data model. So every event will have a timestamp, 2 primary keys, a state, a freshness, and custom key value pairs. So this stayed in French, I'm sorry. So it means event. So the timestamp, the primary keys are host and service. The state is called state, and the freshness is TTL, the time to live. And then we have all these key value pairs. So the idea is to normalize all the events so people who see the events, they know what they're looking at. It's a simple data model, and usually people like it because they know something when it's simple. It's got a state, it has a time to live, it has a host and a service. Basically, the state is always OK. We don't want to flood the user with alerts. So basically, by default, the state is flagged as OK, and warning or critical if we decide so. So we'll come back to that, how we do that, using correlations, the state. Service is, by default, the program name, like SSHD or HTTPD, etc. Or we try to normalize it so that the primary key has something which is close to a primary key, like when we have an event of a failed disk, we will try to make the service look like, for example, kernel driver ATA 2.0. So we know exactly which disk and which driver is concerned. We currently use the same model as collectd. Collectd has this 4 value application instance type instance. It's a convention. For the moment, we're sticking with it. It works quite well. And the freshness is very important. By default, we put 300 seconds. And otherwise, we choose something which has a meaning. For example, we have a pattern which matches users which are being locked out of the system because they failed too many times to log in. And we lock them for 25 minutes. So the TTL is set to 25 minutes. Why? Because when the alert appears in the dashboard, it will stay there for 25 minutes. After 25 minutes, it has no meaning anymore because the user won't be locked anymore. A fresh event sticks in the web browser, and an expired one disappears. Example. So this is a raw message, the same we had before. It's basically an exception from a disk. Normalized, it looks like that in JSON. You can see the timestamp, the host, the service, which fits our data model. So this is done. The transformation is done thanks to the PatternDB parser, which is part of syslog-ng. PatternDB can do correlations. Correlations are very important for us. For example, I was referring to this part, to this message, where a user, myself actually, is locked because I failed too many times to log in. So we have a PatternDB action, which is written as like that. Basically, we have a condition. The condition is, which looks a bit barbaric, but which simply means when context length equals 1, then it triggers the event. This means it will happen only the first time, because every time I log in and I'm locked, the same message will be repeated. And I don't want the on-call engineer to see 10 times the same message. It's stupid. It has no meaning to see the same message 10 times. So we basically create a new event which is displayed only once and which has a time to live of 25 minutes, which is 1,536 seconds, which is actually 25.6 minutes. But I have no idea why we lock exactly that time, but it's like that. And then we put a state warning on this new event, and it will stick in the web browser of the user. So the function of this PatternDB action is trigger one event per locked user, and only one, and have it stick for 25 minutes. Another example, which is a real correlation, as you might understand it, it's messages from, I hope you can see this. Can everybody see it? It's a message from XynetD, the internet daemon. So basically, XynetD, every time it gets its connection, there's one message, which is, even I can see it, so I don't think you can see it. It's start some daemon something, and when the job is done, there's a second message which says exit something else. And so basically we correlate these two events, and we want an alert or a new message to be generated if the two events are too separated in time. For example, we can say that if after 60 seconds there is no exit for start, we get an alert because it means something went wrong or the server is slow or something else. So this is an action. The function of it is trigger an event if XynetD is taking too long to respond. So we have all these rules, all these events coming in, being analyzed, being classified, and the problem with that is it makes a lot of work for me, because when someone says, I want an alert when my service does this and that and something else and correlate it with another event, I have to write the rules. So I didn't want to give this system to users. So when I'm talking about users, it's users in my company. It's not the physicists. It's really sysadmins like me or service administrators like the guys who are handling some SRM system or storage system. So what I wanted to do is make a system where people themselves write the rules. The problem with PatternDB is it's XML and it's quite complicated, so I cannot ask for people to write their own XML rules and stuff. So I came up with a rule delegation scheme. The workflow is the following. People basically look at Kibana in Elasticsearch. They try to find the event which they want to be alerted on. Then they can write a rule which is simplified using a Puppet module we wrote. So there is a Puppet, basically. They're editing a file and pushing it using a Git. Or they can also edit it directly in a web browser using GitLab. Then they write the rules. They push. It gets sent to Puppet. And basically, Puppet tries to deploy the new rule set on the syslog-ng server. And the great thing about PatternDB is that you can test for each rule you're making, you're writing, you can put a list of examples. And these examples will be checked for. And they will be checked for globally with all the rules. So if someone pushes, for example, a pattern which matches all billion logs per day, you have a problem. Well, you don't, because PatternDB will tell you so. It will fail to compile the new pattern database. And so you're safe. And in the case where somebody wrote a rule which is okay, it simply deploys it and it goes into production immediately. This is an example you will certainly not be able to read, but it's basically the 3 steps, the flat message, the matching rule in PatternDB, and the structured message which is coming in. This is the same, but looking at Puppet. Okay, how much time do I have still? 5 minutes, okay, cool. So this is the slide I don't like because it's all the stuff which is not done and needs to be done. Currently we have a little bit of problems using our syslog-ng server. We have message drops. If you have too many messages coming in, it's handling okay if we have 2,000 per second. But if our SRM system goes mad and we get 20,000 per second, we have some drops. Second thing, which is a big problem, not now, but may become one, Kibana is a great interface. Once you show it to someone, he goes like crazy. Oh, I want this, please give me this tool. Great, if it's in our facility, it's okay. But if you give it to someone outside, you don't want them to see all the logs. And Elasticsearch and Riemann have absolutely no way of authenticating people and authorizing people. So everybody sees everything. You can do some segmenting and not allow people to do everything, but you have to do it yourself. It's everything. You have to brew up something using your web server and rewrite requests and everything. So that's a big problem. There's another thing which I'd love to see in the future using in syslog-ng is an automatic pattern tool, which would have some kind of intelligence, some kind of machine learning algorithm, where we could automatically generate new patterns matching messages. I know there's something going on at Blue Waters supercomputer. They have a tool which works quite well. They're happy with, and there's one guy there, Yoshi Fulop, who is very willingly would like to share his code with the open source community, and he would very like to see this in syslog-ng. So I'm sure with the syslog-ng guys we can work something out. And this is the next thing goes with the first one. I think I might in the near future have to use some kind of broker message queuing system to put between syslog-ng and Elasticsearch to have some kind of buffering. And what I'd like to see on the syslog-ng side is an official Elasticsearch destination. because my choice is using Perl for the moment, but it's not ideal. So I'd like to see that. Here are some references you will be able to use if you get the slides. And thank you. I hope that's right. And yeah, some special thanks to the people on here who have really been great, and also thanks a lot for inviting me to this conference. I'm very proud. And
thank you for
guy
coming.
in the back there has been extremely helpful, really. Without him, I couldn't have done half of this stuff. He's just there in the back. Right.
Thank you very much.
Have you received some questions?
Yes. So thank you for your valuable presentation. It was very useful and very interesting. And we have just one question, so please. We need more questions, please. So, how much data flows through your Riemann setup, and how fast? And did you hit any Riemann limits yet?
Okay. So basically, yeah, just because I've been a bit fast, all the data goes to both destinations, Elasticsearch and Riemann. So Elasticsearch is hitting, for the moment, a few thousandths per second limit. As far as Riemann is concerned, I have seen almost no drops. I have about, sometimes even if it goes up to 10, 20,000 events per second, I have no drops. If I have done some micro benchmarking where I saw drops, maybe around 30,000, something like that. What has to be said is on the Riemann side, many of the events are coming in from CollectD using the right Riemann plugin. And the right Riemann plugin currently does not do batching and pipelining. So there are a few issues there which will be solved quite hopefully very soon. And on the syslog-ng side, I think you, the guy who posed the question, should add pipelining and stuff, right? Okay. Oh, another one.
Okay, and next question. Is your Riemann config open source by any chance, or parts of it?
So my Riemann config is like inexistent because there's 3 lines in it. I'm not doing very complicated stuff with it, but maybe you mean the other config, the whole config. So the whole config is completely available, and I've written an article on the subject, which is online on devops.com, which is here, in this list somewhere, the last one. So you can totally grab this stuff, and I've got even a GitHub page where most of the config is.
Okay, and that goes for syslog-ng and collect the configs too, of course.
Yeah.
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 Any other questions?
Can you elaborate a little bit on the considerations behind the data model you presented? So what was the thinking before you came up with this data model, and how happy are you with this data model after using it for a while?
So the choice of the data model is quite evolutionary. At the beginning, I wanted to do something too complex. I mean, I've thought endless hours about the model, how we could, categorize things. I think there was I don't remember the name, but there was a consortium trying to find a data model for stuff. I don't remember the name, but the funding was canceled anyway. So I was trying to find, all these key values which would be standard and people would understand. And I kind of abandoned that because it was too complicated and I was changing around things all the time. And then I spoke to the author of Riemann, he chose that data model, service host, that's all. And he said, I did this simplistic choice on purpose, but it's easy, it's simple, people understand it, and it works quite well. And then I saw the CollectD, how CollectD was doing it, and I thought, yeah, I can just even if I have 5 key value pairs, which I would want to be primary key, I can just serialize them into the service name on a, on a standard fashion. And for the moment, it works quite well. And another benefit of that simple data model is people can actually click on the dashboard. Oh, we take ages. They can actually click on the dashboard to see documentation. So here, there we see our Elasticsearch dashboard. Just for the parenthesis, this spike here is when we did some searches on the Kibana interface. So actually here on the dashboard here, they can click here, and it puts them on the help page using my certificate. And it's probably opened here, file system is full, etc. So using a simple data model, you can do simple documentation as well.
Okay, our time is over for now, but Fabien is coming to our networking party in the evening, so we will have an opportunity to raise more questions to him. Thank you very much, Fabien, for your presentation.